Now we've talked about the factorial function in the previous video. What I want to do is I'm going to give you a couple of examples, typical styles of question that I want you to work through. So have a look at the questions, pause the video, have a ping at them, come back and check your answers here. So here's the three questions I want you to answer. I want you to solve the equation n2 equals 28. I then want you to show that NCR equals NC of n minus r. I then want you to use that fact that we finished the last video on, that nr minus 1 plus nr is equivalent to n plus 1r, to find n in both of those equations there. So pause the video and have a crack at those. So the first question, solve the equation n2 equals 28. Well, the first thing we have to do is take the left hand side and expand it. So we get n factorial over 2 factorial bracket n minus 2 factorial equals 28. So take the 2 factorial over there, because 2 factorial is just 2. We end up getting n factorial over n minus 2 factorial equals 56. Now n factorial over n minus 2 factorial is the equivalent of n times n minus 1 times n minus 2 times then the product of everything after that all the way down to 1. That's then over n minus 2 times n minus 3, so on, all the way down to 1 again. So what we can do is cancel out this section at the top with all of the bottom. So on the top, all I'm then left with is n bracket n minus 1, and that equals 56. Now n bracket n minus 1, if I multiply that out, that's an n squared, it's a quadratic, and we know to solve a quadratic, we get everything on the left, so n squared minus n minus 56 equals 0. Get it equal to 0 and then solve it. You can use the quadratic formula, or you can use everyone's best friend of factorising. In this case, I'm just going to simply factorise it, and I get n minus 8 bracket n plus 7, and that equals 0. So from that, I get the solution that n equals 8, or n equals negative 7. Now, this is the point where logic comes into play. I can't have a negative number in this part of the equation. I can't have a negative number of possible outcomes or a negative number of pool. So I can't have negative 6 racers, for example, or negative 7 colours of choice. So the negative number doesn't work. So from this, I know ultimately that n has to equal 8. Second question, I've got to show that NCR equals NC of n minus r. Look at both sides individually and see how they equate. So I know that NCR is simply n factorial over r factorial bracket n minus r factorial. And if I then look at this side here, I've got n factorial on the top, so great, my top's the same. I've then got n minus r factorial bracket n minus r factorial. Now the n minus r factorial is the same. It's this bit here I've got to muck about with. So if I do that, inside the bracket I get n minus n plus r. So lo and behold, that then equals n factorial over, this bit here is quite simply r factorial bracket n minus r factorial. Excellent. So we've shown what it wants. NCR equals NC of n minus r. This property again is going to come into play a little bit later, purely because it will help us with the number of calculations we've got to do. So if we remember it, great. If not, it might just be a little bit more work for us to do. No big deal. Last question, we're using this fact that we proved. So n r minus 1 plus nr equals n plus 1r to find n in both of these equations. So this equation here, if I look at the left, I've got n1 plus n2. So if I equate this up to these ones here, I know the n's going to stay the same, but if r minus 1 is 1, then r is 2. So that's then going to be the equivalent of n plus 1, 2 equals 28. If I then expand that using the formula on the top, I get n plus 1 factorial, and then on the bottom, I get 2 factorial bracket n plus 1 take away 2 factorial. And I know that that then equals 28. So again, this 2 factorial here is 2. Stick it across and up here, and then let's look at what we can simplify with a fraction. So that then gives me n plus 1 factorial over n minus 1 factorial equals 56 again. So n plus 1 factorial is n plus 1 times n minus 1 times n minus 2 and so forth. The bottom, the n minus 1 factorial is n minus 1 times n minus 2 and so forth. So again, I can cancel out chunks of the top and bottom, and all I'm left with on the top is n plus 1 times n is equal to 56. Now again, if I multiply out this bracket, I get an n squared, so it's a quadratic, same sort of steps. So I get n squared plus n, take away 56, is equal to 0, and again factorise to solve. In this case, I get n plus 8, bracket n minus 7, equals 0. So from that, n equals 7, and I'm not even going to write down the other solution, because n is 7 for here, n is negative 8, so I can disregard the solution from that. So for this one, I know that n has to equal 7. Second one here, the difference is that my n is on the bottom part of it. So I'm just going to have to pay attention to that when I'm working. So if I equate up here, so the n, the top number, is 4. So what that means then is the top number of my new part is going to be 5, whereas the bottom number is going to be quite simply n. And I know that's going to equal 5. So if I then expand it out, I get 5 factorial over n factorial, bracket 5 minus n factorial, equals 5. I want to get rid of the n's on the bottom here, so I'm going to multiply them up to there. But if I then divide through by this 5 factorial is actually going to turn and become 4 factorial. So I know then that 4 factorial equals n factorial, bracket 5 minus n factorial. So I have to find some sort of n, some solution for n here, such that if I take the factorial of it and do 5 minus the n, I'll get 4 factorial. Well, if I do 5 minus 1, that's 4. N factorial, if it's 1, is just equal to 1. What I can then do for that one is quite simply say n has to equal 1. So n has to equal 1 for that one in order for it to work out. So there you go, we've answered that question as well. We've used all the facts that we talked about when it came to this sort of function here. We've used the generic form. We've also used this fact that we've proven, and this identity all comes into play. We have to remember all these little bits when working with a factorial function as we start to apply it to binomial expansions.